have very few non-zero elements. Means that the stiffness matrix or the coefficient matrix will contain only few non-zero elements. The maximum zero elements are zero. Okay, so here we will discuss some advanced and effective methods to get a better solution of the large sparse system of equations. This is our main goal of this presentation. Now we are coming to the concept of sparse matrix. The sparse matrix techniques begin with the idea that the zero elements need not be stored. That means if you have a matrix whose maximum elements are zero, when you are going to store the whole matrix in your computer or in the in your computation, then it will take a lot of memory as well as it will take when you compute the inverse and other things, it will take some lot of time. So to avoid these things, we will use the sparse matrix techniques. In the sparse matrix techniques, only the non-zero element are stored in the computer. Okay, so and there are basically two types of sparse matrix. One is structure, other one is unstructured. So structured sparse matrix means the non-zero entities, whatever the non-zero entities in is in matrix, they are following a regular pattern. Okay, in this case, maybe in the diagonal only the diagonal elements are non-zero, or the tri-diagonal or the pentadiagonal or some banded matrix. So this type of matrix is known as structured sparse matrix. And the unstructured sparse matrix means that will follow a irregular shape. The non-zero elements are scattered. In that case, you can say the sparse matrix is unstructured. Okay, so when unstructured matrix happen, so when you are dealing with a domain which the domain is not regular, not uniform, in that case, the unstructured sparse matrix can happen. So I am showing this by example. Okay, one more interesting thing is that the inverse of a sparse matrix not necessarily to be sparse. Okay, okay. Now coming to this thing figure, you can see this is a domain. It's discretized by the triangulations, and if you impose APM to solve the differential equation in this domain, and then you can get the system of equation where the coefficient matrix will be look like this. Only the diagonal element and some element alongside the diagonal will be non-zero. This is a black portion, and the others will be non-zero. So this type of sparse matrix is known as structured. And if you dealing with the non-uniform domain, so in that case, you can see the non-zero element are scattered. So this is not an example of a sparse matrix. This is not an example of a structured sparse matrix. It is called unstructured. So you can transform the unstructured sparse matrix to structured sparse matrix by using some permutation technique, which is given by the book. In the book, by Yusuf and Sat, you can check there how you can transform the things from unstructured to structure. Okay. Now we are coming to the solution procedure, how we can solve the system of equations. Now to solve the system of equation, there are basically two approaches. First one is direct method and second one is indirect method. So in the direct method, what we do actually, in the direct method, we proceed through a finite number of steps and produce a solution that would be completely accurate. So in the finite, in this each step, we have to do a lot of computation, and that is why the direct method is not that much efficient, because when you have to deal with a large system of equation, in that case, it is not possible to do the lot of calculation. Okay, and that's why the direct method is effective for small system of equations. Okay, and in this category, what are the methods you can put? You can put the LU factorizations, Cholesky factorizations, Gaussian eliminations, etc. These type of methods are known as direct method. Okay, and indirect method, what we do, it produces a sequence of vectors that ideally converges to the solution. That means we start with the initial approximation, and then in each step we modify the each component of that initial approximation, and that in a suitable manner, so that it converges to the solution, actual solution. This is the main goal in the indirect method, and we stop the iteration process when we reach some specified accuracy. Okay, this is the main thing. And indirect methods are always iterative in nature. That means we start with the initial approximation. In each step we modify that, and this is the indirect method, and this is very much efficient for to solve the system of equation when the system is very large. Okay, and also it is applicable when the system of equation is large. Okay, and basically we will discuss this indirect method, which is iterative method in this context. Now we're coming to the condition number. This is very much important in this context, so I should say something. Like suppose X is the solution of the system of equations Ax equal to B. This is our main system Ax equal to B, and X is the solution, suppose. Okay, and we have part of the system by the amount epsilon E into the in A and small epsilon small e in the right hand side B. This is a part of system, and we are considering that X epsilon is the solution of this part of system. Okay, this is our main system, this is our part of system. Now what is our concern here? Our concern is how much it will affect the solution. We have part of in the system, and now we are thinking that okay, we have part of, now how much it will affect the solutions. So for the to know that things, we need some quantity. By we can say that okay, this quantity will measure the how much it will affect the solution. Okay, now to get the things, what we need first, we need the error. We have to calculate the error. Okay, so for that thing, this is the error, delta epsilon equal to x epsilon minus x. This is the error. Now if we put this into the equations, then we get the explicit expression for the error term, delta epsilon equal to this. Now we have to find the relative error. Relative error means the error by the actual value. So this is, you can see the relative error is given by this norm of x epsilon minus x by norm of x, which is less equal to by this quantity. Okay, now if you use the fact that norm of B is less equal to norm of A into norm of x, then you will find the relative error is less equal to epsilon times norm of A into norm of A inverse into this term plus order of epsilon. Now you can see that the relative error is highly dependent on this number, which is known as this quantity denoted by kappa A equal to norm of A into norm of A inverse, which is called the condition number of the matrix. Okay, now what is the importance of condition number in this context? So what I told before, that we need some quantity by this by which we can say that how the system of matrix influenced by some perturbation. So yeah, so you can say that okay, we have determinant value of the system, we have determinant value of the matrix, but the determinant value is never a good indicator. Okay, so here you can say the for large matrices, the determinant of a matrix is almost never a good indication of near singularity, because the determinant value is very much sensitive. If you part of the system, or if you scaling the matrix, in that case the determinant value will be changed, because determinant of A equal to product of the eigenvalues. So that's why the determinant of A is depends very much on a scaling of a matrix, whereas the condition number of a matrix is scaling invariant. Okay, that's why the condition number is much important than the determinant value of a matrix to get the nature of the system of equations. That's why the condition number is important. Now you can see one interesting example here. We have considered A equal to alpha I. I is the identity matrix. So determinant value will be alpha to the power n. Okay, and that will be very small if you consider modulus of alpha is less than 1. That is okay. Okay, now you can say that if modulus of alpha less than 1, then determinant value is very small. Then in that case you can say that okay, inverse matrix will be affected, and it may also affect the solutions. But you can see all the solution will be x equal to 1 by alpha. So the solution is stable. But the thing is, if you judge the system by the condition number, then kappa A will be 1, because determinant A will be alpha and determinant of A inverse will be 1 by alpha, and that will cancel out. So that will be 1. So for any standard norms. So if you judge the system by condition number, then you can say that the system is well forced, right? So we should judge a system of equation or a matrix by its condition number, not its determinant value. And a small condition number implies that a small perturbation in the system leads to a small effect in the solution. That means a small condition number, a matrix have a small condition number, then you can say that if you do a small perturbation in the system, that will affect the small effect in the solutions. And one more thing, the inequality kappa A is always greater equal to 1. Can anyone say that how it can be proved? Because it's very simple. Kappa A equal to norm of A into norm of A inverse. Okay. Okay, so the thing is, answer is that we know that norm of I, the identity matrix is 1, and I equal to A into A inverse. So if you use the Cauchy-Schwarz inequality, that will give you the kappa is always greater equal to 1 for any matrix in any norm. Okay. Now also one more relation related to condition number, which is relative error is less equal to kappa A into norm of I by R by norm of B. R is residual, B minus AX, and a matrix with a large condition number is said to be ill conditioned. Okay, this is the things which related to the condition number. I think you are getting the point why the condition number is important in this context. Okay, now we are coming to the next. Now we are coming to the our main topics of this discussion, which is iterative methods. Now you can classify the indirect method or this iterative method in the three ways. The first one is pointwise iteration. In this category, Jacobi method, Gauss-Seidel method, SOR, SSOR, this type of methods you can put in this category. One more is line-wise iteration, the alternative direction implicit ADI method, stone strongly implicit SSI method. These type of methods that you can categorize in this section. And one more is Kirchhoff subspace method solvers, which is method of steepest descent, conjugate gradient method, generalized minimum ratio, which is known as GMRES. These type of methods are known as Kirchhoff subspace solvers. Basically, we will show that how the method of steepest descent, conjugate gradient, and GMRES works for our system of equations. What is the mechanism behind it, and how it motivated from the basic methods. Okay. Now, the basic concept of iterative methods is that basically we want to solve the system of equations ax equal to b. Okay, we have to find the x. Now, the main idea of the iterative method is the use of splitting technique. That means we will split the matrix A in such a way that we can put some iterations. So suppose A can be written as Q minus A. Okay. Suppose this is a splitting technique in A. Suppose you can split the okay, Q is some matrix and then you can write that in that way. Now, then the original problem can be written in the following equivalent form. The original problem was ax equal to b. You have used that splitting technique, a equal to q minus a, and then ax equal to b will be represented in this form. Okay, qx equal to q minus a into x plus b. That is okay. Now, this suggests an iterative process. So you can put qxk, that the iteration value, the value in the kth iteration, that is equal to q minus a x k minus 1. It is using the k minus 1 iteration value. In this way, you can perform the iteration process. And you are assuming the system has solution, so that means you have to consider the q is non-singular. So if you consider q is non-singular, that means q inverse will exist. So if you multiply q inverse from left hand side, that will give you xk equal to I minus q inverse a x to the power k minus 1 plus q inverse b. So you can guess from here that the convergence criteria will be monitored by this matrix I minus q inverse a. Now I am coming to the point in the next slide. So here you can see if the x is the actual solution, then x will satisfy the approximation x equal to I minus q inverse a x plus q inverse b. Okay. Now you can imagine this as a x is a fixed point of the mapping x to I minus q inverse a x plus q inverse b. So these things you can relate with the fixed point iteration, which for solution procedure for the transcendental equations, okay, or the plane equations. So in the fixed point iteration, what we do, we have an equation fx equal to 0. We write that equation in the form x equal to phi x. There are several choices for phi, and we have to find the suitable phi such a way that the phi prime is modulus of phi prime should be less than 1. This is the criteria for the fixed point iteration. So if you think this iteration process or relate these things with the fixed point iteration, then what will you get? You will get that this norm of xk minus x, this is the error, is less equal to norm of I minus q inverse a to the power k, and norm of x naught minus x. So basically you are thinking that it should be less equal to 1, so that it can converge. And this is the theorem, that if the norm of I minus q inverse a less equal to 1 for some subordinate norm, then the sequence xk converges to the solution ax equal to b for any initial vector x naught. This is the basic concept of some iterative methods. Okay, we use some splitting technique on A such a way that the I minus q inverse A norm of this should be less equal to 1, so that it converges. So there are different choice of q. In the suppose a equal to d plus l plus u, and d is the only diagonal element containing only the diagonal element, l is containing only the lowest strictly lower diagonal, u is containing only the strictly upper diagonal elements. Then in the Jacobi method, you know, we use q equal to d, because in the left hand side we only keep the diagonal element. In the Gauss-Seidel method, we keep only the diagonal element as well as left lower diagonal element in the left hand side. This is Gauss-Seidel method. These are very well known, so I am not going to the mechanism. And SOR method and SSOR method is in the SOR and SSOR Q as given by this. Okay, but we will discuss the SOR method because it is interesting in some point. So SOR method is techniques can be used to accelerate any iterative procedure. SOR means successive over relaxation. This techniques basically we use to accelerate some iterative process. So you can use this for Jacobi method as well as Gauss-Seidel method. These are some basic methods. So you can impose SOR on that method so that it can accelerate your solutions or speed up the solution convergence. Okay. And next, there is a story behind the origin of this method, but the story probably inaccurate. It may be a fake story, but I have added the story here so that it helps us to remember the thing mechanism in our future, because every time we listen the story, that is helps us to remember the things, right? That's why we have added the story here. So the story is that once a dog hunter learned that if he pointed his gun ahead of the dog, he would score more hits than if he pointed right at the dog, because the dog is a moving object, right? So you are trying to hit the dog, so your gun point should be your aim should be ahead of the dog in the direction of its motion. That in this way you can score more, right? This was the thing which learned by a dog hunter, and probably he told his story to his neighbor, and the neighbor was a numerical analyst, and that's why the SOR bonds. Okay, this is the story, and the same technique we will use in the SOR method. How? Okay, let's see. So here SOR is we will use SOR as a refinement of the Gauss-Seidel method. That means we will show that how we can accelerate the convergence of the Gauss-Seidel method. In the Gauss-Seidel method, if you can observe the change in the value of the unknown between two successive iterations, that means you can observe that in two successive iterations there is a changing in the component in the same direction. Okay, and you can guess the direction in the next step. That means you are observing the things and you can guess or anticipate that the same trend will continue on the next iteration. Then why not go ahead and make a correction to the variable? That means when you are guessing that okay, next iteration will be in this way, so before going to the next iteration, if you modify your current value or change some current value, then that will help to accelerate. That will obviously help to accelerate because you are modifying your current value which will be used in the next iterations. So before going to the next iteration, you are changing or modifying the value. Okay, so that's the criteria, that's the way that by which you can modify your or you can speed up your convergence. So in numerical, what we do that xi k plus 1 prime equal to xi k prime plus omega into this. This is the correction. How? This black xi k plus 1, this is the component at the k plus 1th iteration from Gauss-Seidel method. Okay, and this is xi k prime is from SOR. So you have to compute this k plus 1th iteration xi value in SOR. This is the SOR value at kth iteration. You are correcting this value by this term. What is this correction? This is the Gauss-Seidel at k plus 1 and this is the SOR at k. So you are subtracting this value, and by multiplying this omega is the parameter here, you are correcting the value at k term which will be used in the k plus 1. So in this way you can modify the value, and that will known as that is known as the SOR techniques. So here the omega is known as the over relaxation parameter, and the range is defined by 0 less than omega less than 2. And in many computation we need the optimum value by which the best result will show. So to get the optimum value of this parameter, you have to there is a formula which is available in any numerical book. So also in some problems we consider 0 less than omega less than 1. In this interval 0 to 1 we consider omega. So in that case you can say that the method is under relaxation method. Okay. Now we are coming to the quadratic form. So this is the main thing which I am going to discuss. So the quadratic form is defined by f of x equal to half x transpose ax minus b transpose x plus c, where a is the matrix, x are the unknowns, b is the vectors. Okay, and c is a scalar constant. Now if a is symmetric and positive definite, then fx is minimized by the solution to ax equal to b. That means what? That means the apex is a quadratic function, so that will have minimum and maximum. So my claim is that the point by which apex will give the minimum value, that x will be the solution of the system ax equal to b. So our main goal is to find the solution of the system ax equal to b. We are not solving the system. What we are solving, we have to find the minimum point of this function f. That is clear? Okay, so we are not solving x equal to b. We are solving what? We are solving, we are finding the point x for which f will give the minimum. If we get the minimum value, if we get the point for which f will give minimum, that x will be the solutions. And how? Okay, I will show the proof how it is getting the relation is happening. Okay, but before that we need the gradient of a quadratic form. So if fx is the quadratic form, the gradient of fx is defined by this formula. And also we know the gradient is a vector field that points the direction of greatest increase of fx. That means if you have a quadratic form fx and you calculated the gradient, and the gradient will give you a direction, and that direction is what? That direction is the direction in which f will, if is increasing in that direction. So gradient is the direction in which f is increasing. Okay, that is clear. We all know that thing. The gradient is the direction in which f is increasing. Now we are coming to, now what we have to do, we have to find the minimum, the point for which f will give minimum. And to get that thing, we have to set f dash x equal to 0. That is okay, because for any function, if you want to find the minimum point, then you have to put f dash x equal to 0. That is gradient of f equal to 0. Now by a little with a little bit of tedious math, you can compute the derivative of quadratic function. That will give you half a transpose x plus half ax minus b. This is the derivative of f. Now if a is symmetric, then what will happen? If a is symmetric, that means a transpose will be equal to a. Okay, so if a transpose equal to a, that will give you ax minus b, right? So if we put f dash x equal to 0, that means this quantity is equal to 0, and if a is symmetric, that means that will be equal to ax minus b equal to 0. So what is our main system of equations? Okay, so if we a is symmetric, this equation reduces to f dash x equal to ax minus b. That means the solution to ax equal to b is a critical point of fx. That is clear. I have proved that. Okay, so I have to solve the system of equations ax equal to b, but instead of solving this ax equal to b, what we will find the point for which f will give the minimum. Okay, you can ask me that why go to the trouble of converting the linear system into a tougher looking problem, because just we have to solve ax equal to b, and there are a lot of methods by which we can solve the system. But why you are getting this type of things by introducing quadratic function, and you want to find the minimum of that quadratic function? It is quite seeming like laborious, right? So but it is, though it is seems like laborious, but actually it's not. If you can understand the mechanism, then that will be only 3-4 lines algorithm by which you can compute the things in your computations. Okay, that will be very easy, but this is a mechanism that's why we need the quadratic function and all these things, gradient and minimum. Okay, now you can see, if I have plotted the things in the 2-dimension case, suppose x1 in direction, x2 in this direction. So if you consider in the R2 or the 2-dimension case, then the fx will be looks like this. This is one type of parabola, and this is the quadratic function for different values of x1, x2. Okay, and you can see this is the minimum point will be somewhere in the bottom, and you have to go there, you have to find that point in which for which f will be minimum. And the initial approximation, you have to start with some initial approximation, because it is iterative methods. So obviously you will start with an initial approximation. So your initial approximation should be somewhere in the above, here or here. Then you have to go down, slide down, and then you have to reach the minimum point. Okay, now how you will go down and reach the minimum point, this is the main mechanism, and this that will give by the steepest descent and the conjugate gradient. Okay, now this is the contour plot. Okay, if this is the minimum point where you have to reach, and you can start with an initial guess with somewhere in the here or here. Okay, okay, Here you can see if A is positive definite matrix, then the figure will be looks like this. If A is negative definite matrix, then the figure will be look like this. In that case, the maximum point you can find out. In this for positive definite, that will give the minimum point. For negative definite, that will give the maximum point. And if A is singular in that case and positive indefinite, then you know that there may be two things can happen. That one is no solution, one is infinitely many solutions. In that case, you will get infinitely many solution because the through the bottom lines which is in this valley will give you the solution. Any point in this line will give you the solutions, and in this case that will be saddle point. So in that case, the steepest descent or the CG, or that means conjugate gradient, will not work. Okay. So basically, we will consider that A is positive symmetric, positive definite matrix and symmetric. That is will work for CG and steepest descent. Now we are coming to the method of steepest descent, the mechanism. That means we will start with an arbitrary point x naught and slide down to the bottom of the paraboloid. Okay, and that will be occurred by the series of steps x1, x2 until we are satisfied that we close enough to the solution x. Okay, so these things you can relate with a practical example. Suppose you are in a paraboloid type structured stadium and you are watching a game, and suppose you have find that you find that one of your friend has seated in bottom somewhere in the gallery, and you want to reach them him. And what you have to do, obviously you can't jump over the audience, so what you have to do, you have to find a way by which you can reach your friend, and the way should be should contain the minimum step, right? So this is the actual mechanism in the method of steepest descent. So the x naught, the initial approximation, is your position, and the actual solution x is your friend's position. So you have to reach your friend by some path that will give you x1, x2, x3 until convergence. Now you are in a position x naught, and but you have to start your you have to change your position, but in which direction you should change your position, right? And we know that f prime x, which is the gradient is the direction in which f is increasing its value. So but we have to get the minimum point, so we should go in the direction in which the opposite to f dash xi, because opposite of f dash xi means minus of f dash xi, and minus of f dash xi means the minus of gradient direction, and which is the direction in which f is decreasing. Okay, because I have to reach the minimum point, so I should go in the direction of minus f dash xi. So also we have proved that f dash xi equal to was axi minus b. Okay, so minus, if we multiply with minus, then that will give you b of b minus axi. This is the relation that will needed in the future. Now let's get familiar with few relations. So error ei equal to xi minus x. This is the vector that indicates how far we are from the solutions. Okay. Also this ri is the residual equal to b minus xi. That indicates how far we are from the correct value of b. Okay. And there is a relation between ei and ri, the error and the residual. What is that relation? The relation is ri equal to minus a ei. This is the relations. Okay. One more thing is that we have already defined that ri equal to minus f dash xi, because f dash xi is a gradient direction, that is equal to a minus bxi, that is equal to the minus of residual. That means ri equal to minus f dash xi. So what is indicates, we have to go in the negative direction of the gradient, this direction, and this equals to ri. That means we have to go to the direction of residual. Okay, so in each step we will go to the direction of residual. This is clear? Okay, that is the direction of the steepest descent. This direction is known as the steepest descent. Okay, that means we have our initial approximation x naught. We have to reach our next destination x1. The x1 will be given by x naught plus alpha r naught. R naught is the residual, because we have to go in that direction r naught. This is okay. But the question is, how big a step should we take? Because we are not we cannot go blindly to in that direction. Somewhere we have to stop and we have to change our direction. That is also applicable in the stadium example. Okay, you can't you have to somewhere in the state and you have to take a right and then left. In this way you have to go. So we have get our first direction that we have to go to our in the direction of residual, but how much I should go and then stop and then I have to change the direction, that I have to find, right? So we choose alpha in such a way that alpha that minimize the f along a line. So to get that thing, again we have to derivative f of x1 with respect to alpha, and that we have to put equal to 0. That will give some relation by which we can get the value of alpha. Okay, so if we derivative, we can use the chain rule. So using the chain rule, we can get the derivation that is given by f dash x1 transpose r naught. This is f dash x1 gradient of f at the point x1, and this is residual at the previous iterations. So what is showing that these two, if we put equal to 0, that means this is f dash x1 and r naught should be orthogonal. Okay, so alpha should be chosen so that r naught, the previous residual, and the current gradient should be orthogonal. Okay, this is the main mechanism of the steepest descent. So you can see somewhere in the here we have started the initial approximation x0. It is going in this direction, it is x1, and now the previous residual and the new gradient is orthogonal. So it has changed its direction. It has x2, again x3, x4. In this way it is converging to x. This is the steepest gradient, and the zigzag path is occurring because in every step each gradient is orthogonal to its previous gradient. That's why the zigzag path you can show. One more drawback is here that from x0 to x1 the direction is same as when you are x2 to x3, or you can say x1 to x2 the direction is same as x3 to x4. After one iteration it is taking the same direction. Why? Because we have used the relation orthogonal. So as you are using the orthogonal direction, that's why they are using the same path one after one, same direction. Okay, so this is a drawback. You can see that from here, if you take the direction directly from onto x, then you can reach the x directly, but you are not taking the direction, you are taking the orthogonal. So this is the drawback in the steepest descent, and this is the motivation for the that is the motivation for the conjugate gradient method. From that conjugate gradient method is established. And now we are coming to the algorithm, steepest descent algorithm. So this is you can see only 4 to 5 algorithm. Whatever the mechanism was there, but when you are computing the solution by using steepest descent, you have to only 3-4 lines codings. So first you have to compute the residual, which is r equal to b minus ax and p equal to ar. Then you have to replace alpha by this r comma r inner product by p comma r inner product, and then you have to replace x by x plus alpha, and also replace residual by r minus alpha p. Then if you compute p equal to ar, then you just do the same things until the convergence. Okay, now we are coming to the conjugate gradients method. What I have told that there is a drawback in the steepest descent. What was the drawback? Because we were taking the same direction one by one, from x0 to x1, then again x3 to x4, then again x5 to x6. In this way we are taking the same direction. So what would be better if every time we took a step we got it right at the first time. That means in each step we will make a new step, new direction, which we will not traverse it in before. Okay, so in each step, in every step we should find a new direction. That is the conjugate gradient methods. Now here is an idea. First you have already find a set of orthogonal such directions. Just before the computation, you find that okay, I have in orthogonal such direction, and in each step we will follow one by one. That is d0 d1 to dn minus 1, all the orthogonal directions, but they are not the same directions. And in each step you will find one. First one d0, then you will find d1, then you will use d2. In this way that will goes, and the xi plus 1 will be xi plus alpha di. This is the in each step you choose a point like this. This is the, you can see the previous one was in the direction of r0 or ri, the residual direction. Here it is replaced by di. Di is not your ri, not your residual. Okay, this is the difference. In the steepest descent the direction was residual direction. In the conjugate gradients method the direction is the new direction. That I have not explicitly stated here, but I will show that what is the direction. Now the question is how we can find alpha high. here, because in the previous, the steepest descent, how we find alpha, we derivative alpha, we derivative f with respect to alpha, that will equal to 0, that will give you alpha in the steepest descent. But if you do the same thing here, then it will give the orthogonal direction again, but we are not finding the orthogonal direction. So there should be some new condition. The new condition is that the error ei plus 1 should be orthogonal to di. This is a new condition by which you can find the alpha I. Okay, the ei plus 1 is the error in the I plus 1th iteration, that should be orthogonal to your previous direction di. Now if we put that condition equal to 0, that will give you alpha equal to minus di transpose ei by dit into di. Okay, now there is a problem. Problem is what? If you want to compute alpha I, you have to know ei. But if you know the ei, then you have already solved the problem, because unless you compute alpha I, you do not get xi, and and then you can't compute ei. So you have to remove ei from here, because unless you know ei, you can't compute alpha, but you have to compute alpha I first, then you will get ei. Okay, so what can be the solution? The solution is that we have stated that ei plus 1 should be orthogonal to di. Change the thing. You just use the not orthogonal. It should be a orthogonal. A orthogonal, which is the conjugate actually. So what is the definition of a orthogonal? Di and dj are two vectors. If they are a orthogonal or conjugate, that means they are satisfying this relation dit a dj equal to 0. So if it's just orthogonal, that means their a will be not there, just dit into dj will be equal to 0. A orthogonal means there will be a between them. This is the definition of a orthogonal. So this relation will be imposed in that place. So if I impose the relation, then what will happen? So ei plus 1 be a orthogonal to di. So if we impose the relations, then that will give you alpha equal to this. Now there was ei, and we know the relation a ei equal to ri. Okay, so you can put that a ei equal to ri. So you can see in the ith iteration, you know all the values. Di is already predefined its reaction, ri is a residual, a is in your hand. So all the things you know, so you can compute alpha I. So okay, now it's cleared. Now only the thing is that I did not define the di, the direction, search direction. Okay, so okay, one more thing is, you can see here that if you search vector this di, if you put its residual direction, then that will be same as the steepest descent, what we did in the steepest descent method. Okay, now all that is needed now is set of a orthogonal search direction di. So orthogonal direction is finding orthogonal direction is very easy, but a orthogonal direction, finding a orthogonal direction is somewhere it is a little bit tedious. So but fortunately there is a simple way to generate them called a conjugate Gram-Schmidt process. In the usual Gram-Schmidt process, what we do, we have linearly independent vectors, and we can transform this set to a orthogonal set. This is the Gram-Schmidt process. The conjugate Gram-Schmidt process saying that we have n independent vectors, then we can transform this into n a orthogonal set of vectors. Okay, this is the conjugate Gram-Schmidt process. This is available or given in the papers by Jonathan, so you can see there. Okay, this is quite laborious or quite big. So in the conjugate gradients is simply that the method of conjugate direction where the search direction are constructed by conjugation of the residuals. So we are not taking the search direction as the residuals, we are constructing the direction in the linear combination of the residuals. We had our previous residual, now we have our new residuals. Okay, we are not going to the previous and new, we will go in a direction by the linear combination of these two residuals. This is the that will be our new search direction. Okay, in this direction we will go and we'll find the minimum point. And okay, now you can ask that it is well defined, or this choice makes sense or not. So that choice makes sense for mainly two reasons. First one is the The residual work for the steepest descent. So why not for conjugate directions? One is that, and the second one is that the residual has a nice property that is orthogonal to its previous search direction. So it is guaranteed always to produce a new linearly independent search direction. And if it's giving me the linearly independent search direction by using Gram-Schmidt conjugate Gram-Schmidt orthogonal process, we can produce the A orthogonal direction by which we can go forward. Okay. Now the major advance in is what makes CG is as important algorithm is that the space complexity and the time complexity per iteration are reduced. So from order of n squared to order of m, where m is the number of non-zero entities of A. So in the conjugate gradient method, the very less iteration is needed, and also it takes very few times rather than the others method that I will show by some code, okay, in the practical computation. Now this is the algorithm for the conjugate gradient method. See what was the mechanism was there, but you can see only 3-4 lines coding, only 3-4 lines algorithm is in the conjugate method algorithm. So first you have to compute that. First you have started with the residual direction, okay, and then you are computing alpha I by using that techniques. Then your next iteration point xi plus 1 will be in the direction of di up to alpha I. The alpha is given here. Then again you have to compute the residual Ri plus 1, and then you have to compute this coefficient by the conjugate Gram-Schmidt orthogonalization process. Once you get the beta I plus 1, by using this you can get the new direction di plus 1. In this direction you can put in your again here, and then you will get the next. In this way you can get the solutions. Okay. Now, sometimes the name conjugate gradients mislead the readers because the gradients are not conjugate here. Because okay, and also the conjugate directions are not all gradients. What we are doing that we are finding a new such direction that will be the linear combination of the previous two gradient. So that means conjugated gradients would be the more accurate name. Okay, the thing is like that. And here is the plotting. So you have started with the x naught. In the steepest descent you have seen that somewhere in the here they have turned to the orthogonal direction, again turn orthogonal. In this way he reached the x. But in the conjugate gradient they are not taking the orthogonal direction, they are taking the a orthogonal direction, that is conjugate directions, and that means from x1 they can directly reach to x. This is the benefit in the conjugate gradient method. Now we are coming to the projection methods. So whatever I discussed in previous, the steepest descent and the conjugate method, that are also one type of projection methods that you can establish by theoretical aspects. But I showed the geometrical point of view. Okay, the idea of projection technique is to extract an approximate solution to the above problem from a subspace of Rn. Okay, I will first generate a subspace of Rn, then I will try to extract an approximate solution from that subspace. So what is the mechanism? Suppose script K is the subspace, which is search subspace from where you will extract the solution. But suppose the subspace has this dimension m. So in general you need m constant must be imposed, right? Because you are you want to extract the approximation and the dimension is m, so you obviously it will take m constant. And but the question is how you can impose that m condition. A typical way of describing this constant is to impose m independent orthogonality condition. Okay, so you have a search subspace, the dimension is m, and you need m constants. Okay, you give the m independent orthogonality condition by which you can find out the solution. Now this defines another subspace L of dimension m, which will be called the subspace of constants. So this m linearly orthogonality condition will contains in this subspace script L. That will call your subspace of constants. Okay. Now there are two type of projection method. One is orthogonal, other one is oblique. In the orthogonal projection method, what do you do? The subspace script L is the same as script K. That means your search subspace and the constant subspace are equal in the orthogonal. And in the orthogonal projection means what we did in the steepest descent. And oblique projection method, that means it is used in the conjugate gradient CG method. In the oblique projection, the script L is defined from the script K. This is, or maybe totally unrelated. You can use some defined L or K. Okay, so this type of method is known as the oblique projection method. Now we are coming to the Krylov subspace method. So Krylov subspace method is one type of projection process, projection method, and these techniques are based on projection processes and both orthogonal and oblique. Okay, on to Krylov subspace. So your search subspace will be your Krylov subspace. This is the main thing. And what is Krylov subspace? Now, Krylov subspace are spanned by vectors of the form PA into V, where P is a polynomial. Okay, so P is a polynomial, so P of A will be a polynomial of matrix A that will operate on V, and the span by this vector that will give you Krylov subspace. And in short, this techniques actually what they do, they approximate A inverse B, because I have to find the A inverse B to get the solutions, but they do the A inverse by, they approximate A inverse by P of A, where P is a good polynomial. So the solution will be looks like P of A into B. This is the main things in the Krylov subspace. Okay. In general, we define the Krylov subspace as following. This is your one type of Krylov subspace where K, whose dimension is M. So this is spanned by V, AV, A square V up to A M minus 1 V. This is one type of Krylov subspace. And GMR is one type of Krylov space solvers, which is generalized minimum residual method, where we use that kappa equal to kappa, script k equal to script km, and script a l equal to, this is your constant space, this is your search subspace. This subspace is the your Krylov subspace, and the space of constants is equal to the script km. Is the km is the mth Krylov subspace, where you can see that this is defined by V. So you need a V. V is the residual by the norm of residual. This is used in the GMREs, and I am not showing the algorithm or the detailed GMREs in this presentation, because that needs many things from the linear algebra. And now some references here. This is Jonathan's paper, then Yusuf Saad iterative methods for sparse linear systems. This is some CFD books, and this is Kinketchen numerical book, where I have collected the things. Okay, so now I will show from the practical point of view. Okay, before that, if anyone have any doubt or any questions.
Hello.
Hello.
Yes, Bhaiya. Bhaiya, in each and every method, the matrix should be in the, non-singular form, right?
Yeah, the matrix should be non-singular.
Yeah, in each and every method,
yes,
right?
because you are finding the unique solution, no? That's why the
Yes.
matrix should be non-singular.
And one more thing, in the iterative method, we are writing A in the form of Q minus A, right? So the capital Q will be, any kind of special form. The form of Q will be any kind.
Yeah, you have to find the Q in such a way that the I minus Q inverse A, the norm of this should be less equal to 1, because that is the reason by which you can get the convergence. Okay, now there are several choice for, you can get the several choice for Q, but you have to find a suitable choice. Like for Jacobi method, you
Jacobi
choose
method we are writing in the diagonal. Yes.
Yeah. There are various choice, and depending on the various choice, you will get the convergence in different ways.
Okay, so it has some kind of limitations, right?
Yeah, definitely.
Okay. Thank you.
This is called the preconditioner. Okay. So in order to speed up the convergence, we can use, this is called the preconditioner. Okay.
Yeah.
So if we are not using somewhere that condition number of the matrix may not be good. So by using the preconditioner, we can speed up and we can change it. That is that way that for different methods, you see the precondition are different. For example, here simply diagonal matrix, then diagonal plus the lower triangular. So by that way.
Yes.
Okay, they are all preconditioners.
Okay, so
Hello.
hello.
I have a doubt that
whenever you are finding that condition number, so we need the norm of A inverse, right? So
Yes, yes.
if A inverse is suppose unknown, it may be unknown sometimes. So how to find
If
that?
you have,
The norm.
if you have A, then you if A is, if you consider A is non-singular, then you will find the A inverse, no?
Yes. No, means for large case, like means computationally we can find it through MATLAB or something. Yeah.
That means you are saying that
Hello.
your system of equation is large and you have A,
Yes,
but
yes.
as your system equation is large, so you can't compute A inverse.
Yes,
So how
yes.
can you get the norm of A
Yeah, by
inverse?
hand.
Yeah.
Yes, yes,
So
yes.
if you don't, if you can't compute the A inverse, in that case, how can you compute the condition number? So in that case, you can't
Yes.
get the condition number, because to get the condition number, you have to find the A inverse, and then you have to find the norm, and then you have to multiply the norm of A into norm of A inverse.
Okay. In slide number 35, can
35.
you go to slide number? Yeah.
Yeah. Okay.
If yeah, here you are writing that f dash x1, then in right side f dash x1 transpose. How? Because of
I
hello.
this thing, this here.
Yeah,
Okay, I
f
have
dash
put
x1
the
and f dash
transpose
transpose.
to yeah, I have put in the transpose to show that the vector multiplication actually. So one is both are row vector. Okay, so by one row, one column, that is the way to get the equal to 0. That will give you the orthogonality condition. That's why I put it the transpose, because that will be equal to 0, and from that you will get the orthogonal condition. Okay, so that both are row vector, and that's why I just wanted to show that the transpose, you have to use one transpose, otherwise the multiplication is not defined.
Okay. Another last question, that in case of some matrix, suppose it is not M matrix, so you mentioned something like permutation we have to use to change it
I
to.
mentioned permutation to get the from the unstructured to structured sparse matrix, because suppose what you have, okay, let me show. Suppose you have an unstructured sparse matrix. In that case, you can use the permutation technique to get the sparse matrix. Okay, but not that you have a not you don't have a M matrix. You use some permutation to get the M matrix. Not that way. So in this way, you
No,
whatever the,
can't do it. Can we use that permutation to get
no.
means
To get the M
like
matrix, you have,
elementary matrix is something like this, elementary operation.
what is elementary operation? I did not get it. What?
Element
What?
like elementary of suppose we have a matrix A which is not a kind of M matrix. Suppose
Okay.
one column or one other terms are non negative, less than equals to 0. Suppose one row or one column is giving some different values, say suppose positive value, then can we transfer it to some elementary
If
matrix?
you use the elementary operation, after the elementary operation, the nature and the characteristic will be same, because when we have a matrix and we use some elementary matrix, we use the elementary matrix to get the reduced form or some echelon form or like this. Okay, so whatever the matrix
Yes.
will form after the elementary operation, that will the nature of this matrix will be the same. So I don't think that you can change the matrix by elementary computation, by elementary operation to a M matrix. So if your matrix is not M matrix, then you if you use the elementary operation, that will also will be the same,
Okay.
because after the
Okay.
elementary operation, the nature of the matrix is the same. Both are equivalent, na?
Yeah, element. Okay.
So any more question?
Yes, Bia.
Yeah.
I have last question. The method of steepest descent method. So
Yeah.
this is a kind of a we are finding minimize the shortest path, right?
Yes.
So this is a kind of means numerical method to find a sorted distance between like initial point to.
Yes, you have to find the shortest distance, but you, as you are suppose in a paraboloid or this type of shape, so you can directly jump. You have to go through that the surface. Okay, so that's why you are going down, then you are changing your direction. In this way, you have to go only. You are not like you are now x naught and directly you can jump into your actual solution. Not it is not possible. So you have to find some successive way, x1, x2, x3. In this way, you can only go to your actual solution.
Okay.
But the process is,
So
yes,
iterations we can go.
yes, and the thing is you have to minimize the f because you have to reach the minimum point. This is the main
Yes.
under of the that steepest descent.
Okay. Thank you.
Yeah, sir, my question is regarding the condition number.
Okay.
So we say that if the condition number is low, then it is a well conditioned system.
Yes.
So and the condition number can be any real positive real number. So how can I say that for this particular problem I can take this much of condition number? Means if it is 100, so it is low for that particular problem, or it is high for that particular problem. Is there any interval that I can consider it to be a low for the particular problem or something?
No, what you can say is that your condition number suppose is low, means suppose 1 to 5 or 1 to 10. In that case, you can say that if you part of the system, that will affect small, because if your condition number is 100 or 150, that will also affect, but the effect will be very large. In this way you can say, but you can say that the condition number is low, that means suppose 5 or 10, that will be your very well posed problem. In this way you can say the thing, you can say that if your condition number is small, then the problem will be that the perturbation effect will be small. If your condition number is big, that in that case the perturbation effect will be big. But there is no interval in which suppose k kappa is belongs to 1 to 5, then there will be, that is a very good system of equation for a particular matrix. This type of theorem is not exist.
Okay.
So you cannot change the condition number of the matrix. Okay. In general, the condition number is reasonably good. That way we will tell. It will never be less than 1. Even for the identity matrix, the condition number will be equal to 1. Okay. Therefore, and then you can't change the condition number. And in general, for all the problems, the condition number will be reasonably good. That's all. Okay. But some sensitive problem and then this unstable problems, you can see the condition number will be very bad. That way you can see in the MATLAB, when that will give you still the answer, the solution, but it will tell the matrix is badly scaled. Yes. Okay, then the matrix is near to singular. And those cases, we have to use SVD-like methods, singular value decomposition and all to solve. Okay, but generally the advantage of these methods, the Credo-Subspace methods, these are all based on the optimization. That is minimizing the residual. Okay, so here the advantage is, if I am having the system of size, let us say million by million, within million iterations, the convergence is guaranteed.
Yeah, that I will show by method.
That is the main thing. Okay. And the second thing, if you are using any iterative methods like Gauss-Seidel or direct method like Gauss elimination, LU decomposition and all, there the computational cost will be very high, because we have to store the matrix. Then we have the space will occupy. The number of operations, if you see, the arithmetic operations, for example, your this Kramer's rule, which we will be good in doing by manually, 3 by 3 matrix, 4 by 4 matrix system. But the number of operations, if you see, that will be n plus 1 factorial. Okay, then you can imagine if the matrix size is 1000 or million, then how much time it will require. Okay, then your Gauss elimination will be order of n cube, your Gauss-Seidel will be order of n square, and all the number of operations. But here, the convergence is guaranteed, and in general, we may not get always the symmetric matrix. So that is the reason we are having this biconjugate gradient method. There are a lot of variants of the conjugate gradient. Okay, and then you are having this GM-REST, generalized minimum residual. Okay, they are all, even for the non-symmetric matrices, we will have that. Okay, and another thing, Here we don't need to store the matrix at all. Okay, with an initial vector V0, if you take something, then the subspace, we will generate the Credo subspace. There, that will be the product of AV0, AV1 like that. So product of a matrix with a vector, we have to store only a vector. Okay, so by that way, we can save the storage also. That is why these are all computationally very efficient methods. Okay, yeah, go ahead.
Okay, thank you, sir.
Any more question?
Yeah, I have one more question.
Yes.
Can you go page number 32?
32. Yes.
Yes. In this diagram, you are saying the quadratic form for a positive definite matrix, it has a like in the part A minimization, right? So it
Yes,
is
yes.
always true in each and every case, A, B, C, D.
Yes, if you have the positive definite matrix and the matrix is symmetric, then it will have the minimum.
So is there any case for semi-definite matrices also?
Semi-definite.
Yes, yes.
So in that case, no, I have not searched that thing. So I have to get whether it is I can get or not.
Okay, okay.
But I have to find. Yeah. Any other question?
Vijit.
Yeah.
So while you are describing this ill-conditioned matrix,
Yes.
I think you can define this condition number of a matrix by using the singular values also. So somewhere I have studied that the condition number of a matrix is given by the ratio of the largest singular value to the smallest singular value.
Largest singular value means?
Singular value decomposition of a matrix. Suppose this is some numerical linear algebra technique.
Okay, yeah.
So,
no, that will be the ratio between the largest and then the smallest eigenvalues.
Eigenvalues, yes.
No, I think they are singular values of the matrix.
No,
the ratio of the largest singular value by largest singular value by smallest singular value, and the determinant of the matrix is given by the product of those singular values. So if a matrix is very close to singularity, so at least their product will be close to 0, and this is due to the singular smallest singular value will be very close to 0. So therefore the condition number will be very large because you are dividing by a very small number.
Yeah.
Okay. So in that way also we can think that the matrix is ill-conditioned. Although it is theoretically this matrix is showing that it is non-singular, but due to the smallest singular value tending to 0, we can say that these computations may be unstable.
Okay. Yeah, that can be a way to represent the condition number.
Yes.
The second thing they can see that Sachin asked some question and all. You can read the optimization book to the matrix. Okay, that the quadratic form, the matrix of this quadratic form is symmetric and positive definite. We can correspondingly we can see the function that okay, it is this convex, and then it has some conditions I forgot. Then even the nonlinear problem, we will have that condition when we make this even the Kundakar theorem and all. Okay, so
yes,
that will lead to
a
convex function, and then we will have a unique minimum. That is the reason we are able to use these methods. Okay, so that we can see some optimization books. Not optimization means you people all think that is LPP. That is not only optimization. That is the operation research. Okay, so the optimization we have to see. Okay, there are very good books are there. Even that book itself that I already shared you the folder, that also you can have the look.
Yes, sir. There are some discussions like Kuhn-Tucker points. So those problems actually.
That are all for the nonlinear optimization problems.
Nonlinear, yes, nonlinear programming problems. NLPP.
Yes. So there we have to find the, again everywhere that minimizing that loss or the maximizing the profit, that is the one, but here that minimizing the residual. Okay. So again that the function should be convex, so that the symmetry and then that positive definite will ensure that. Yeah. Is it done, Abhijit?
No, I want to show.
Sure. Yeah, go ahead.
Okay. So suppose I have a 2 cross 2 matrix. Okay. Now A is 5 1 1 2, and the right hand side is given by B. This 2 2 2 2. Okay. And also we have some initial approximation. Suppose this is 1 and 2. Now I will show that I will run the each method, Gauss-Jacobi, Gauss-Seidel, S/O, steepest descent, conjugate gradient, and I will show that a conjugate gradient will only need 2 iteration to converge. Okay. Now first I will starting with Gauss-Jacobi. The program is there, and if you use the Gauss-Jacobi, then you can see. Okay, I'm coming to later. Okay. So it is taking 7 iteration with the initial approximation 0,1 and the root is 0,22, 0.88. The time is taking by 0.2 seconds. Okay. So in the Gauss-Jacobi, it is taking 7 iterations. If you use the Gauss-Seidel iteration, then again it is taking 7 iteration and the required root is reached. And you can see here this is your initial approximation somewhere there, and it's coming from that in that direction. Now if you zoom it, then you can find there is some more iteration is there, because it has 7 iteration. Okay, this is your actual solutions. Okay, now we are coming to the SOR method. Okay, this is your SOR method. This is taking again 7 iteration and time is taking 0.1 second, and the roots are converging in this way. From the initial approximation is coming to this, and then again.
No, we are not seeing any slide. Are you showing that the method of steepest descent slide is there? Are you showing something else, or in the slide only you are explaining?
No, I am showing from MATLAB. I don't know. Okay, wait.
You have to share, I think.
Well, I am not seeing anything on my screen. I thought that may be a problem with my computer.
Okay, wait.
No, sir.
I think now it's okay. Is it showing my MATLAB interface?
Yes, now it's okay.
Yeah, now you repeat from that beginning.
Okay. So suppose I have a matrix A, 2 cross 2 matrix 5 1 1 2. Right hand side is defined by this, and initial approximation is this. Okay. Now I have to find the solution of the system of equation 2 cross 2. Now first I will use the Gauss-Jacobi. So this is your Gauss-Jacobi method. It is converging in 7 iterations, and the required root is 0.22, 0.88. Time is taking by 0.22. Now if we use the okay, so is it possible to see the graph? Can you see the plot?
No, it is not yet come. Okay, you have to share everything.
How can I share everything? There is any option?
I think
one by one you have to share. It is not coming, na? Because we are seeing only the MATLAB window.
Okay.
You have to go to the figure and then you have to show that.
Okay, sir. Let's keep the figure. I will only show the computation. So this is taking 7 iteration. In the figure, you can see that how coming from 0,1 to the path, how it's going. Okay, because by figure I can show that in the steepest descent, in every iteration it is taking the orthogonal direction. That's why I plotted that thing. Okay, no need. So Gauss-Jacobi is taking 7 iteration. Now if we use the Gauss-Seidel, and it is taking again 7 iterations. If you use SOR, it's taking 7 iterations. Okay, but if you use a conjugate gradient, then you can see it is taking only 2 iterations, because 2 cross 2 matrix, so n iteration will be sufficient. So only 2 iteration it is reaching the exact solution by only 0.07 seconds. So this is the benefit by the conjugate gradients. This is the things you can get in the conjugate gradients method. Okay, so if you have a large system of equations, so in that way also you can use the conjugate gradient to get the solution in a faster way, because it reduces your computational complexity. This is the thing I wanted to show by coding. All the existing methods are taking time, or also it's taking iterations number, a large iteration number, but conjugate gradients only taking 2 iterations.
Yeah, but if they want to see the real effect of that, then they have to take the large systems. Okay,
Yes.
maybe they have to take some
I did
2
not take
dimensional elliptic PDE.
Yes.
Then they have to discretize. Then they have to see. Then they will be able to feel really the effectiveness of the methods.
Yes. Actually, I have taken that 2x2 to show the plot actually.
Yeah, that is okay. No, that
Yeah.
is okay for your presentation purposes. Fine, no problem.
Yes.
But I am telling in general, if they wanted to see, then they have to go for the larger system to take.
Yes.
Then they can feel that the computation time, they can calculate everything.
Yes. Actually, in our research, we have to use the 1024 or 2048 mesh points. So in that case, the system of equation arises. It has the 1024 into 1024 dimension. So if you want to solve the thing, you should use the conjugate gradients or GMREs by conjugate in all these things. Okay, it's over. So if anyone have any inquiry or questions, they can ask, or we can finish it.
Yeah, I think you all will go through the material what I provided, and then try to make the code. Then only you feel the comfortable and you will get more confidence. Okay. I think there is no other questions. I think Sandeep can wind up.
Yeah, Sandeep is the coordinator, so he should.
Yes.
Okay, sir. Then we can.
And maybe they can ask Desta, where Desta has left already, or to give some next seminar or some talk.
Okay, so Dixa message me that send me the all the materials. Okay, I will share all these things with everyone, the slide and the other things. Also, if you want to get the convergence of the steepest descent and the conjugate gradient, then you can follow the Jonathan's paper. There is only 30 to 40 pages paper, and everything was well written in that paper. That is basically use the eigenvalue and eigenvector approach to get the convergence.
Yeah, I think they are in the department of Vijit.
No, sir, I am at the home.
Oh, nobody in the department, all of including me. Okay, then. So if not, so good night to all. So take care. So maybe we'll see in the next seminar.
Yeah, okay, sir. Thank you.
Good night.
We can finish it, Mrityunjay, that part.
Which one, sir?
Mrityunjay has turned off, I think.
Which point?
मृत्युंजय को शायद कुछ उसका रिसर्च के बारे में बोल रहे थे सर.
अच्छा.
Okay, so
Okay, thank you, very thank you.
Bye. Good night.
Good night.
Bye. Good night.